Okay, now we're going to use the terminology and the knowledges and the facts that we have learned in earlier sections in chapter 3, including the subspaces and the lines and planes, etc. Linear independent. Okay, section 3.5, solution sets and matrices. In this section, we state the relationship between invertibility of matrices and solutions to systems of linear equations. Okay? Here, if A is an invertible matrix of size n, then AX equal B has a unique solution, which is this. Is it right? Since we have A inverse, so just multiply A inverse on both sides, then we have X is equal to A inverse B. Clear? Okay? The following system can be written as AX is equal to B, like this. Okay? So which can be written in a matrix form, like this. Then find the A inverse, like what we did before. Then just multiply A inverse on B. Then we have the solution X. Easy. And also here, suppose you have a matrix and vector, then we find the inverse matrix and just multiply this inverse matrix to the B vector. Then we have a solution. So we compare those two solutions, this solution and solve the linear system of equation. We check the solutions are same. So it's easy. If the linear system has an inverse, just find the inverse, then multiply to solve the linear system of equation. Here, homogeneous linear system of equations like this, then can be written in this way. Here, where AX0 is. Then in this case, X is equal to 0 is a trivial solution. It is a solution always for the homogeneous system of equation. But the solution which is not a zero vector is called a non-trivial solution. Since homogeneous linear system always has a trivial solution, it only has two cases for the solution set. It has only, the linear system of equation has only a trivial solution or either or it has infinite many solutions. Infinitely many solutions. Okay? It has infinite many non-trivial solutions. So instead of three cases, because it always have a solution, we only have two cases. That's it. Okay, now, a homogeneous system with m equations and n variables such that m is less than n has always non-trivial solutions. If we have more variables than the number of equations in a homogeneous linear system of equation, then it always has an infinitely many solutions. Infinitely many solutions. Okay, so this I explained the meaning of this theorem. Okay, homogeneous linear system like this has the following augmented matrix and its RREF. Okay, this system of linear equation has this matrix. Then we form this is augmented matrix, and then RREF of A looks like this. Here, then we have free variables like this. So the corresponding linear equations like this, and we have two free variables. Let that be the R. This R and S. Then we have what? We have the variable. We have x1 and x2 and x3 and x4 can be written in this way. So any vectors that satisfies this for any R, scalar R in real are the solutions. So clearly, the solution has a non-trivial solution, which is a non-zero vector. It's always. So if you find the RREF of the given linear system of equation of homogeneous system, you can easily see where it has a free variables or not. Okay, then this is important. The associated homogeneous system of linear equations. Given a linear system of equations, AX is equal to B, then AX is equal to 0 is called the associated homogeneous system of linear equation of AX is equal to B, like this. This is linear system of equation, AX is equal to B, then associated homogeneous linear system can be written in this way. Okay. Okay. Then from here, you can easily find the RREF of this, and from here, you see it has the free variables from here, so you can find the infinite many solutions of this homogeneous system of equation. The problem is, then what is the whole set of solution for the original non-homogeneous system of equations? That's it. So from here are the free variables. With these free variables, we have this linear system. We have this set of solutions for the associated homogeneous system. Then think about this augmented matrix. The whole. Okay. So this is the solution set for the homogeneous system. Homogeneous system. Then next thing is we are looking for the whole solution set for the non-homogeneous system that was originally given. Then what you have to do is just find one solution. Find one particular solution that satisfies that homogeneous system. Then all you have to do is just add this particular solution to this set of solutions to have the whole set of solutions for the given non-homogeneous system of equations. So the solution for this is the solution set for the homogeneous system. This is the particular solution for the homogeneous system. Here I'm going to explain the relationship between those two, the particular solution and the solution set for the homogeneous system to the solution set for the non-homogeneous system. Here, you see. Here, W. This W is this is a set of vectors that satisfies AX is equal to 0. So this W is a subspace because it has a 0, the origin in it. If you add X0 plus W, then this set is a kind of transition from here to here. This is a solution for the AX is equal to 0, and this is a solution set for AX is equal to B, because any vector is in here satisfies this non-homogeneous system. So when you are asked to find this set of solution, then all you have to do is find the solution set for this homogeneous system easily and find just one particular solution in here and just add it. Add this vector to the solution set of homogeneous system. Then you have the whole solution set for the given non-homogeneous system of equations. Okay? Mm-hmm. But this is not a subspace of Rn. Why? Because origin, 0 vector, is not in here. It's been moved up by K, by X0. Okay? So this is subspace. This is not subspace. Okay. Yeah, we're going to, here, so now we can expand the equivalence theorem. Yeah. For a matrix A, the following are equivalent. RREF of A is identity, and A is a product of elementary matrices. A is invertible. 0 is the unique solution to the homogeneous system, and AX equal B has a unique solution for any particular B. Okay. And the columns of A are linearly independent, and rows of A are linearly independent. And so this is very important. If these are the columns are linearly independent, which you can find it by using the REF of a given matrix, then you can say whether this linear system of equation has a unique solution or not. Here, the vector of the solution space of AX equals 0 are also orthogonal to the rows of A. AX equals 0 can be written in this way. Columns, the rows of A and vector. So what this means is the inner product of this times this means the inner product of AN and the vector X is 0, and inner product of A2 and X is 0, and inner product of AM, X is equal to 0. Rows, what this means is rows of A are orthogonal to X if this homogeneous system has a solution. Okay. So the vector in the solution space of AX equals 0. If any vector satisfies this, then it should satisfy this and this. What this means is these vectors should be also normal to any row vectors of A. Okay, now we consider these three linear system applications. And these linear systems, and it is easy to check whether these are the non-trivial solution of this system. Okay, just find the very simple solution. Then let us verify that V is also orthogonal to the row vectors of coefficient of A of the above system. Easy. Then make a matrix, then give the solution vector here, then find the dot product with the inner product and dot product with V on of row 1, row 2, and row 3. As you see, they are all zeros. They are all also orthogonal. You can easily check it. This is last. Hyperplane. Line of XY plane. Okay, the solution set of a linear equation. A1x plus A2y is equal to P, where at least one of these coefficients are not 0, A1, A2. Then this represents a line. Plane of XY, G plane. The solution set of linear equation this, where this sum of AI's are not 0. Then this represents a plane in R3. What is hyperplane then? The solution set of this equation. If where sum of AI's are not 0. This means there exists I such that AI is not equal to 0. So for some AI is not 0. That satisfies this. Then in that case, the solution set of this is form a hyperplane in Rn. Let's say, but if B is 0, then it's a hyperplane passes through the origin. Because if this is 0, then 0, 0, 0 is a solution. So 0 vector is in the solution set. So in that case, that hyperplane passing through the origin. Anyway, what this means is a solution set. What this means is the inner product of A vector with AI's and this vector X, which is formed by X1 and X2 and Xn, is inner product is equal to 0. This is orthogonal. And A is not a 0 vector. And so the solution set that satisfies this is a hyperplane. So we denote it as a perv. Hyperplane. And this set, the solution set that satisfies this is called an orthogonal complement of a vector A. So if you have a non-zero vector A, then the set of solutions for this equation is called the orthogonal complement of A. What this means is if we have a plane here, then this plane can be represented by this equation. And this orthogonal complement is the one which is orthogonal to that plane. The vectors orthogonal to that plane. This is called the orthogonal complement. So if we have a vector here, if we have a vector n here, then the vectors which is orthogonal, the set of vectors this is orthogonal to this vector n is what? If a non-zero vector like this or like this, then the set of vectors that is orthogonal to this vector, so which forms a plane like this. So if you have a non-zero vector like this, then this plane means the orthogonal complement of this n. So this plane pi represents the orthogonal complement of this normal vector n. And also, this plane can be written as this, like this, ax plus by plus cg is equal to b, like this, isn't it? So this can be written as ax plus by plus cg is equal to b as a plane. I think that's the end of section 3.5. And 3.6 is a special matrix that introduces diagonal matrix, identity matrix, scalar matrix, and tridiagonal matrices. So that's very simple. Okay. I think we will clear this chapter 3 in the next class. Any questions?